Good morning, everyone, and welcome to the GISS Sea Level Rise seminar. We're very glad to have Dr. Vivien Gornitz. She is a scientific analyst at Autonomic Integra LLC, and she's affiliated with the Center for Climate Systems Research at Columbia University and the NASA Goddard Institute for Space Studies. She has a bachelor's degree from Barnard College and her PhD from Columbia University. And her research interests include sea level rise on various timescales and regions, impacts of rising seas and storm flooding on the coastal zone, and more recently, the effects of climate change on the cryosphere. She's a member of the New York City panel on climate change and has contributed to the New York State Energy Research and Development Authority report. And she's also a coordinating lead author for climate change and cities for the second assessment report of the Urban Climate Change Research Network, and has been a contributing author to the IPCC reports in 1990, 1995, 2001, and 2007. And she has written and edited several books, including Rising Seas, Past, Present, and Future, and Vanishing Ice, Glaciers, Ice Sheets, and Rising Seas. Today, she will be speaking on the topic dams, sea level rise, and downstream coastal impacts. So welcome, Vivien.
Okay. Yeah, this was one of my interests a long time ago, actually, and I've come back to it more recently. And land water storage represents a small but not insignificant part of the contributing factors to global sea level rise. And in since the 2000s, roughly comparable to that of glaciers and the Greenland Ice Sheet. And to have a precise closure of the sea level budget, therefore, also requires knowledge of changes in land water storage, both climatic and anthropogenic. My particular interest has been more on the anthropogenic changes, and that's what we will focus on in the next slide. I'm having an issue here. I'm not advanced. Oh, here we go. All right. So land water storage can change either through climate driven changes in precipitation, temperature, and so forth, as well as anthropogenic changes in land water storage, the most important of which are water being retained on land through dams and reservoirs, or being returned back to the ocean by excess groundwater extraction, also known as groundwater depletion, overdraft, or groundwater mining. The other land use changes are just a very minor part of the total. The numbers shown here on this slide represent the distribution of water on land. As you see, glaciers and ice caps capture the greatest amount. Groundwater takes up close to a third. The balance in lakes, rivers, marshes, soil, permafrost only constitute around 1% of fresh water. And here's just the schematic diagram of the water cycle, including human interventions. And water is evaporated from the ocean and driven by winds and air currents to land, precipitates on land in the form of rain or snow, and is returned back to the ocean either by melting of ice and glaciers and permafrost and rainfall that runs off into the rivers back into the ocean. Now, humans have played a growing role in changing this natural water cycle as mentioned before, largely through building of dams, excess removal of groundwater, and also other forms of land use change. And here are various estimates of the contribution to global sea level rise from changes in land water storage over the periods indicated. And as you can see, if you examine the centennial scale, there's a negative contribution, largely because of dams withholding water from the ocean. But after the 50s through 70s on to the present, you have an increasing positive contribution, mainly from the growing role of groundwater overdrafts. And the role in the future will be much smaller. This is based on the IPCC projections, 2100 relative to the more recent period, because of the growing contributions of ice melt from both glaciers and the ice sheets. And so therefore, the land water storage change will be much, much smaller. Furthermore, the period of dam building will have ended, and presumably people will learn to manage to handle their water resources without depleting them. So in recent decades, total land water storage represents, as I mentioned, roughly about 10% of the total sea level contribution from various sources. Here you see the way it has, the anthropogenic changes since the mid-20th century. And what is shown in the net change is here in the middle in pink, and the trend is downward, meaning that more water is being released to the ocean than is retained on land, because this represents the land water component on that remains on land. Here's the role of dams. There is an increasing amount of water being withheld by dams, but that is overshadowed by the role of groundwater over extraction. And here we're looking more closely at dam building and reservoirs, again, for various time periods. This is the contribution to sea level. As you can see, again, if you look on the centennial scale, there's this overall negative trend showing the greater influence of dams in the earlier part of the 20th century, but becoming more negative. In other words, more water being here in this case released to the ocean because of groundwater extraction. And again, the role will increase slightly in the future, in the near future, because of dams. Now, here, this is just a survey of various dam databases that are used in compilations to estimate the water held by dams. And the ones outlined in purple are the most important of the two. The most widely used is that grand version 1.3, which has over 7,000 reservoirs and sizes greater than 1/10 of a cubic kilometer. More recently, just this year, earlier this year, a new database, GDAT, has been published, which has records of about 35,000 reservoirs, of which 32,000 roughly are georeferenced, also taking those water bodies that are greater than a tenth of a cubic kilometer. Not all of these are actually used in computations, because I think that in the paper by Zhang and Gu, that they have cut off very early dams that are built before a certain period, and those of the last few years, so that the actual number that they're using is somewhat less than this. And in conjunction with that, you have these hydrological databases that cover lakes, rivers, and basins in great detail. And these are some of the characteristics in these databases that are useful for this type of study. And here you see, for example, a map showing all of the lakes in hydrolakes. And you'll see quite a large concentration in the Arctic regions due to thaw ponds and small lakes. No particular distinction at this point is made between reservoirs and natural lakes. Here is the location of dams and their catchments in GDAT. Here you'll see a much greater concentration in areas, in regions below the Arctic areas. And here it's a much vaster compilation of actual reservoirs, artificial water bodies. And these are their catchment areas, the areas that are draining into those reservoirs. And for those that are interested in the way this would work in the GISS GCM, I would refer to both Gary Russell, who has created these maps, and also to Joy Romansky that are working with them in their research, and can give you more explicit details of how it works in the model. But anyway, the arrows, they're barely visible in these various cells, indicate the directions of river flow as compiled in this map. And here's another map, an analogous map, which includes for each of the grid cells the fraction of that cell that is covered by a lake or water body. And in calculations of the contribution of dams and reservoirs to sea level, one important factor is that of the storage of the actual storage in the reservoir. And these reservoirs are normally filled approximately to 85% of total capacity, typically. But of course, the actual volume at any given time can vary for a variety of reasons, both due to natural climate, rainfall and such, and also evaporation. But the evaporation from lakes and reservoirs has been estimated to be relatively minor, contributing just a small amount to global sea level rise, just a fraction of a millimeter a year, hundredths of a millimeter a year. Although more local losses can be extremely high, as in Lake Mead and Lake Powell in the Southwest. And I've seen those lakes as recently, I think, as 2017, and you could see the bathtub rings around them. And I think they really reached a minimum. Lake Mead at only 27% capacity in 2022. However, a more recent study seems to imply that there's a much more important lake volume decrease that they've noted in about 53% of the lakes that they examined, which we'll see in a moment. Seepage, that is to say percolation of water beneath the reservoir, can be calculated at 5% when the dam is complete and filled, and then perhaps 5% times the square root of time after X number of years. And so that's fairly well known. Siltation has generally been overlooked, and this is something that I'm looking at more closely in a simple calculation I'm just showing in the next slide. Now here's the decline in lake water storage according to Yao et al. And the positive trends, where there's significant losses, are shown in red. The darker red represent natural lakes. The paler pink circles represent reservoirs. The blue represents those which are actually gaining in volume rather than retreating. And then overall, you could see there's a general loss in water storage in reservoirs as well as natural lakes. Some of it coming from evaporation, and others, particularly in reservoirs, they attribute those losses to siltation. And here's just a quick calculation, assuming the general reservoir storage capacity on the order of 6,000 to 8,000 cubic kilometers based on various studies. And for three siltation rates, 0.3 to 0.9% a year. And even at the lowest rates, after 50 to 100 years, you have a significant reduction in the capacity of the reservoir. So that got me interested in downstream impacts of the dams. And one of them is, of course, changes in stream flow. And that can be studied, through the model in terms of examining the climatic factors, generally precipitation, but also evaporation and transport, evaporation and transport or evaporation. And but interestingly, given the sediment retention in reservoirs, there is a loss in sediment being carried downstream by the river, which some people have proposed will contribute to an increasing loss in delta area and ultimately submergence. And that would increase coastal vulnerability of deltaic communities to storm surge and sea level rise. And there are considerable numbers of people living in the flood zone of deltas, and that is what raised a lot of concern. And so, however, there's a lot of things that can affect river flow, various anthropogenic activities. Of course, we've mentioned dams, but there's also urbanization, sand mining, irrigation, and removal of coastal vegetation, drainage of swamps and coastal wetlands, and again, fluid over extraction, not only groundwater, but also in many cases oil and gas. I mean, that's particularly the case in the Mississippi River Delta. So here's a map and graph showing the percent of sediment loss since the 1970s relative to the pre-70s period for the deltas indicated on the map. And some of the rivers that were most affected are rivers like the Nile, the Chao Phraya in Thailand, Mississippi, Red River in Vietnam, Pearl Yellow in China, and so on. Less affected are those at the tail end of this scale. Now, if all the dams that are planned and are built reach their maximum storage capacity, there is potentially further loss of sediment loads due to the retention in the reservoirs. And again, some of the most highly affected rivers would be the Volta, Nile, let's see, Chao Phraya again, the Mekong, and well, to a lesser extent as you go down the list. And many of the areas that would be most affected are in Southeast Asia and China. Now here's another figure showing the delta land area change due to sea level rise from a study by Nienhuis and Van der Wal. And the thing there is that they, contrary to a lot of other studies, maintain that most of the deltas are currently gaining area rather than losing, except as you see here in the Mississippi Delta, which is a special case. But with projected sea level rise, according to the RCP 2.6, 4.5, and 8.5 scenarios toward the end of the century, as these increase, with increasing sea level rise, more and more of the deltas stand to lose land rather than gain. And so in other words, they would attribute that mostly to the rise in sea level rather than changes that human activities are making. But regardless, I mean, even if, let's say, in another study, they show a dominant loss of delta area at present, if these sea level rise scenarios come to fruition, as the rise increases, more and more deltas will be in danger, regardless of human activities or not. Now, multiple factors are contributing to delta subsidence at present, both geologic and anthropogenic. And there's always a deep-seated land subsidence because rivers and deltas form in areas where land has been subsiding for millennia, if not for millions of years. More recently, from a geologic point of view, you have sediment compaction as recent sediments settle down and are compressed by overloads of newer, fresher sediment. You also have a neotectonic activity and a glacial isostatic adjustment. In addition to that, you have anthropogenic activities. We mentioned the role of dams and fluid extraction, but also engineering works like dikes and levees and canals and river dredging for shipping. And also generally overlooked are things like river and beach sand mining, the sand being taken to make concrete and other uses for urban activities. And then you also have land use changes, urbanization, deforestation, and clearance of deltaic wetlands. And here's an attempt to look at these deltas, to rank them by hazards, exposure to hazard, and anthropogenic drivers. And this is shown in this chart B below. which is kind of complicated because what they're calling anthropogenic conditioning index really represents a measure of anthropogenic caused relative sea level rise. So it would include both natural and whatever other factors contribute to relative sea level rise on the horizontal axis. The vertical axis, what they call a hazardous event index, is really exposure to storm surge flooding. And so in the upper right quadrant, you have deltas that are most at risk to both the relative sea level rise and to the flood exposure, including rivers like familiar rivers like the Yangtze, Mississippi, Pearl, Ganges, Brahmaputra, and Indus, whereas less affected by flooding, although I would dispute that of Chao Phraya in Thailand and Irrawaddy in Myanmar, which sustained a major cyclonic event not that many years ago. So anyway, so they also would be at high risk to these natural factors. Now here you have rolled in not only these factors mentioned before, but an additional factor, IDI, that represents the ability or non-ability to increase coastal resilience based on socioeconomic factors of the country in which the deltas are situated, and their ability, the financial ability to enhance the coastal resiliency. And by that standard, the most exposed are rivers like the Ganges, Brahmaputra, Irrawaddy, Volta, Yangtze. And as you go down the list, Mississippi ranks low because of the ability to create dikes and levees and other protective measures. And the other rivers like Mackenzie and Yukon are on the bottom of the list because they're not at particular risk to these other factors. And here's another way of representing this. Again, looking at the relative sea level rise exposure versus the ability of the country in which the delta is situated to increase their resiliency. And so this would be an increasing risk factor here in red, increased exposure to risk. Here in the middle area is both increase in exposure and vulnerability, but so this doesn't look at the it takes into account these various factors, and so again, some of them most vulnerable to both exposure and risk would be the Mississippi, Rhine, Yangtze, Pearl, and Indus, and Mekong is sort of on the borderline, and so on. So these are various attempts to examine various factors affecting deltas in the future and their exposure to rising sea level. Now, looking at the multitude of factors that can cause delta subsidence, we look at the Mississippi Delta in greater detail, and we look at various factors. This is one of the lobes of the Mississippi Delta. By the way, it has been losing area, as you could see in one of these earlier slides here. Here, this picture here is a satellite view, a Landsat view of the most seaward extension of the Mississippi Delta, and you can look how ragged it is, how chewed up it looks, literally because of the land loss that it has sustained. And so here, in the absence of dams, this particular area would be gaining land. And these are just various scenarios. What if you only look at the role of dams? Here, you're still gaining area, but at a much lower rate. By adding in levees, you're reducing the land area. If you combine dams and levees, it's even worse. And then you're looking at the actual observation, which is lower than all of these. Well, this would be the sum of all of these put together. So according to Edmonds and all, dams don't play as important a role, according to them, as the construction of levees, which prevent overflow of sediment into the surrounding areas. The sediment is discharged directly into the Gulf of Mexico instead of spilling over and building up the surrounding delta area. Here you're comparing various land use activities to deep subsidence, which I don't know why there should be a peak in deep subsidence around 1960-ish, but I could see why there may be a peak in oil and gas and water extraction in recent decades. And here you see some combined effect of land loss shown here. The effect of levees in this brownish color, the effect of dams in pink, much less, and this is the combination of two in the middle curve. So to summarize, total land water storage changes, this includes both climatic and anthropogenic, is roughly 10% of global mean sea level rise. Total land water storage has been increasing since the 70s, largely from groundwater overdrafts. The dam contribution to global mean sea level peaked in the 50s to early 2000s and has been much less since the 2000s. The grand version 1.3 and GDAT are the most comprehensive up-to-date dam databases. Hydrosheds would be your best source for data on lakes, rivers, and basins. Reservoir storage volume losses will affect your estimates of land water storage, and sediment sequestration in reservoirs may curb downstream sediment load and lead to delta mass loss with rising sea level, but many other factors, once you reach the delta, many other factors come into play. And we have examined some of those. And so that the losses of sediment due to dams is just one, and it may be a small part of the total change in delta stability, which in the future will be governed more and more by sea level rise. And further research will be needed on projecting both the climatic and anthropogenic drivers of land water storage, and also develop methods of analyzing this complex interplay between the human causes and climatic causes of groundwater and dams, in as far as land water storage change is involved. Okay, that is basically what I have to say. All right, are there any questions?
We have Natasha clapping. Some other people.
Everything clear?
So yeah, I had a question about like the climate models and the extent to which climate models or Earth system models capture these processes, like in future projections.
Well, I'm really not the best person to ask of how these are handled in the model. Maybe if Joy is on today, I don't know if she's on, may have another word or two to say about that.
I am here. I don't know if Gary is here. Gary might also be oh, Gary is here. Please feel free to chime in. The GISS model does not at present capture dams at all. We are working on implementing the amount of water stored in dams in the correct location. Rivers are not strictly represented. We have flow between boxes, flow of water between boxes. So we wouldn't, grid boxes, we wouldn't put a dam per se, but we would represent the amount of water impounded by dams. And that is under development, and hopefully we'll get a sense of how that affects the GISS climate. Going forward for future projections, that seems a lot trickier. How are we going to know where the dams are in the future? I don't know. I mean, if we have an idea where they might be, we may be able to do that. But I think right now we're working on historical dam water impoundment as our next step. I hope that answers your question.
Yes. And I think Gary, did you want to?
I could just say the lakes group were studying things like, it appears that like there's like these wetlands and river areas that contain water on the sides of the rivers, and wetlands which are not really properly covered by the model. We think there's not there should be more water stored in the Amazon basin, and it seems like most of it seems to run off into the Amazon and run out into the ocean, as opposed to being stored a little more regularly on the on the continent. I don't know. That's about all I have to say.
Okay. Any other questions? So I guess related to that, when people are making projections or estimates of local sea level rise impacts, is this something that's taken into account? I guess, I don't know if you...
Well, I think that may be the case for certain areas, certain delta areas. where you have high populations or other economic activities. I know that certainly in the Mississippi Delta, which with which I'm more familiar with than some of those in Asia, that they have documented very carefully land loss over time, and they know a relative sea level rise. I think there has been some debate in the past as to what are the causes of land loss in the Delta. You know, at one point, you know, there are authors who will claim that the upstream damming had a big effect. Now, more recently, as you could see in one of the studies we showed, that they emphasize the importance of levees. And you have a lot of anthropogenic activities going on in the Delta that have changed it, modified it over time. There has been canal dredging. There has been clearance of wetlands in some cases, definitely a lot of oil and gas extraction. And so all of these have impacted the Delta. The question is in what proportions?
Seems like it might be something people should study more. Okay. Well, if we have no other questions, I guess we can stop there. Anybody else?
Okay, well, thank you.
Yeah, thanks very much,
Okay,
Vivien.
okay.